Welcome to VLSI design video. We are looking into the unit 4, which is floor planning and placement. This is the lecture 6. In the previous videos, I have given you in detail about all the remaining 5 lectures of floor planning and placement. The objective of this video lecture is to explore the SoC details, system on chip details like I/O architecture and pad design. So we'll discuss first about the I/O architecture. I/O is input-output architecture on a chip or a floor, which is used for placing the design what we are designed to. So the pads and their associated drivers are distributed around the edge of the chip. Pads here are I/O pads, input-output pads or input-output ports, and their associated drivers are distributed around the edge of the chip. I have shown you in the first lecture beginning slide when I explained you about the terms, floor planning terms. I have shown you. Advanced high density packaging schemes devote a layer of metal to pads and distribute them across the entire chip face. Face I mean to say here, the face is the one where we can see. So face I mean to say on the surroundings or where you can see out, not internally. Each pad must be large enough to have a wire or a solder bump soldered to it. It must also include input or output circuitry as appropriate. So here you can see in the diagram, these are the I/O pads which are located at the face. Face means where you can see, not inside or inside the core. What is a pad frame? Each pad is built to a standard width and height for simplicity. Each pad has large VDD and VSS lines running through it. You can see here in the each pad has a large VDD and a VSS running through it that you can see in the architecture of the pad frame. A pad includes a large piece of metal to which the external wire is soldered. If the pad requires external circuitry, it is usually put on the side of the pad closest to the chip core. The chip core fits in the middle of the pad ring. So you can see the chip core is in the middle of the pad ring. This is the pad ring. So the chip core is in the middle. So if the pad ring is not completely filled with pads, spacers are added to keep the power lines connected. So spacing between the pads has to be kept if it is not completely filled, so that in between we can pass on the power lines. The placement of pads around the ring is usually determined by the required order of pins on the package. Generally, whenever you design something and you are going to make out a chip, for that chip you will be even placing the pins. So these pins are to pass the signals or to give some input-output lines and so on. So the placement of the pads around the ring is usually determined by the required order of the pins on the package. The wires to the package cannot be crossed without danger of shorting. So if the package pins are required in a certain order, the pads must be arranged in that order. The order of pins on the package determines routability of the board and electrical noise among other things. The order of pins on a package has been known to determine which candidate design wins a design contest. So the pad is much larger than any single wire. Just remember, pad is not just a single wire, it is much larger than that single wire which is connected to it. So the current in each direction is limited by the outgoing wire. If you want to use multiple power pins to limit inductive voltage drop, we can use several VDD and VSS pads around the ring. So these pads can be even used for passive VDD and VSS, but they are not called as IO pads. They will be called as supply pads. So I have shown you in the slide that there are some pads which are called as bonded pads. VDD and VSS pads are the easiest pads to design because they require no circuitry. Each is a blob of metal connected to the appropriate ring. So now moving on to the pad design, pads and pad circuitry. For designing a pad, we need pads and pad circuitry. Pads used for input and output signal requires different supporting circuitry. A pad used for both input and output, sometimes known as a tri-state pin. Its trade name is tri-state pin 1. Combines elements of both inputs and output pad. So what are input pads? The input pad may include circuitry to shift voltage levels or otherwise condition the signal. The main job of an input pad is to protect the chip core from the static electricity. So this is the main job of an input pad, to protect the chip core from the static electricity. People or equipment can easily deliver a large static voltage to a pin when handling a chip. So that's why the main job is to protect the chip core from static electricity. The MOS circuits are particularly sensitive to static discharge because they use thin oxide. The gate oxide, which may be a few hundred angstroms thick, can be totally destroyed by a single static jolt, shorting the transistor's gate to its channel. And input pads put protective circuitry between the pad itself and the transistor gates in the chip core. Electrostatic discharge can cause two types of problems. They are dielectric rupture and charge injection. So we need to take care with the input pads. So these input pads should not cause the electrostatic discharge or ESD problem. When the dielectric ruptures, chip structures can short together. Okay, this is the problem with the dielectric rupture. So the dielectric rupture, that means the dielectric is melting up. Then the chip structures, what all we have inside it, can short together or come together. The charge injection is the other problem with that. An electrostatic discharge event can be sufficient to damage the small on-chip devices because charge is injected into it. What is that charge? The charge is nothing but electrostatic discharge. So if that is injected by an ESD, then it may damage some on-chip devices, small on-chip devices. What about output pads? Electrostatic discharge protection is not needed for an output pad because the pad is not connected to any transistor gate, whereas input pads are connected to transistor gate, because we know on a chip we take the count as transistor count, and all the MOSFETs will operate with the gate voltage. So to the gate we need to give the input. That means it is again given to the input pads. So input pads will result in the electrostatic discharge, whereas output is what we are taking outside. We are not giving the supply, we are taking the output line. We are not giving the supply. So this will not cause any electrostatic discharge. So there is no need of electrostatic discharge protection. The main job of an output pad is to drive the large capacitances seen on the output pin. Within the chip, lambda scaling ensures that we can use smaller and smaller transistors, but the real world doesn't shrink along with our chip's channel length. So this is an output pad. As I shown you, the darker area is an output pad. Here the input is given through a buffer or input can be directly given through an input pad. So since the inputs are connected to the gates, you can see to the PMOS gate as well as to the NMOS gates, there comes the electrostatic discharge. So, but if you use wide output drivers, then they drive these MOSFETs, then the output, the connection between these two MOSFETs you can see are given to the output, and that is connected to the output pad. So this output pad, if these wires are too long or this wire is giving you some parasitics, then this will result in some parasitic capacitance or inductance. There is a three-state pad circuitry. Three-state pads used for both input and output. Pad cannot used as an input and output simultaneously. Chip core is responsible for switching between modes, like for switching as an input and for chip switching as an output pad. Pad requires electrostatic discharge protection for when the pad is used as input. That's what we were discussing previously. An output driver for when it is used as an output, plus circuitry to switch the pad between input and output modes. We need a output driver. So if input mode is 1, you can see here, this is the input mode. When it is 1, what happens? There is a 0 which is given here. So when 0 is connected to a NAND gate, it will be always 1. So when it is always 1, that means it is always off. Okay. So when this is always open, then we need to look at this connection. So the data out, which is given here between these two connections, now that will be passed here and will make this MOSFET either to be on or to be off, so that we can use this wide output drivers, the pads, as a switching either to pass it. See, if the input mode is 1, what is happening? It is acting as an input pad or as an output pad that we are supposed to see. So when the input mode is 1, so this is going to be 1 always, that means this is off. So here the signal is passed from the input mode to this NOR gate, and only one MOSFET is working, so it acts as a input pad only. Otherwise it acts as an output pad, not together, not both at the same time. What is the boundary scan for pads? Pads may also include circuitry to support boundary scan, which configures the chip's pin as an LSSD chain. Chips that support boundary scan can be chained to form a single scan path for all the chips on a printed circuit board. Boundary scan is nothing but scanning all the devices on the boundary. Generally, on the boundaries, we connect all the chips. So each and every chip has its own ID, IC, or a small data signal, or a shift register. They have its own ID. So when I want to pass some signal, each and every with its ID has scanned, and we see that whether they are allowing the signal to pass or not. That is what is called as boundary scan. So here, since at the boundaries as a phase, we have seen in the diagram, IO pads are kept. So we can use these IO pads for boundary scan also. So the boundary scan makes the printed circuit board much easier to test because it makes the chips separately observable and controllable. Boundary scan support requires some circuitry on the pins corresponding to the chip's primary inputs and outputs, along with a small controller and a few pins dedicated to boundary scan configuration. So I hope you have understood what is IO pad or IO architecture. In the IO architecture, we have seen about the IO pads. Then this IO pad, if they are separate, like only input pad, only output pad, what are the problems? And a three-state pad circuitry we have seen. The three-state pad is 1, only as a high impedance or only the data out, or with the input mode it can be made to act as a input pad or output pad or only high impedance. So that is called as a three-state pad. And we have seen how to use these pads for the boundary scan. And the boundary scan is important for testability or testing the chip. So these pads which are located as a face or as a circle or a boundary on the chip can be used for the boundary score or for testing that particular chip. So I hope you have understood all these things from the unit 4, that is the floor planning and testing, how to plan and placement, floor planning and placement, in that how to place the devices, how to supply the clock and the power, and some of the parameters related to floor planning and placement. Thank you for watching.